Okay, so what we're going to do now is we're going to work on Section 4.4, which is customized doses, based on calculating doses of based on weight, also based on the body surface area, and then we're going to calculate some pediatric doses as well. So most manufacturers, of course, of drugs offer dose ranges as prescribing guidelines. In some cases, the suggested dose may be based on a patient's weight or the patient's weight and height. And a good example of this, when you go to the store to get, say, children's liquid Tylenol, usually they're based on the patient's weight, sometimes their age and weight. So it is important, of course, for parental, pediatric, or geriatric doses. Okay, so children and the elderly, of course, are going to need more customized doses because, of course, they weigh significantly less than the normal adult patients do, and the drinks are designed for that, and they're designated for that as well. So medications with low margin of safety will usually be based on your weight. Usually milligrams is the most common unit that's going to be used of medications per kilogram of body weight. So some manufacturers, of course, will offer prescribing guidelines for a medication based upon a therapeutic amount or range per unit of body weight. So this is an example of, and I'm going to show it to you in part 1 and part 2. So a patient weighs 60 kilograms and she is to receive a medication of 15 milligrams per kilogram. What will her dose be? If the medication is available in a 300 milligram capsule, how many will be dispensed? So what you're going to do first is determine the dose, and then second you're going to determine the number of capsules to be dispensed. So kind of to show you how to do that. For part 1, determine the dose using the ratio proportion method is what you'll do. So we know we have X. You'll know how many, of course, will be dispensed. First, what will her dose be? So we know we're going to have X milligrams. Okay, and the patient weighs 60 kilograms. Okay, so if you look into your word problem, she is to receive a medication of 15 milligrams per 1 kilogram. So you have milligrams on top, so you have milligrams on top, so you put your 15 milligrams on top, and your 1 kilogram on the bottom because you have kilograms on the bottom over here. Okay, so then what you want to do is you want to do cross multiplying. X times 1 always goes on the bottom. It'll be 1x or just 1. 15 times 60, of course, would be 900. 900 divided by 1 would be 900 milligrams. So her dose is going to be 900 milligrams of medication for her body weight of 60 kilograms. So next, you want to determine, of course, the number of capsules to be dispensed using the ratio proportion method. So we know her dose is going to be 900 milligrams. Okay, we're trying to find X capsules. Okay, so if you look up here, the medication is available in 300 milligram capsules, which could be worded 300 milligrams per 1 capsule. So if you have milligrams on the bottom here, you have to have your milligrams on the bottom here. So you have 300. And then, of course, per 1 capsule would be on top. You have capsule here on the numerator, capsules over here. So then you do your cross multiplication. X times 300 is 300. 900 times 1 is 900. And you can simplify by taking out the zeros if you want. And 9 divided by 3 would be 3 capsules. Okay, so next we'll do a couple of problems out of the book. If you look in your book on page 102, I think number 11, Um, so you have here the cortisone is dosed. It says calculate the following weight-based doses based on the provided recommended dose, round to the 100th place. So I'm not going to write this on the board, but I'll work the problem out with you. So cortisone is dosed at 0.5 milligrams per kilogram per day. If the patient weighs 56 kilograms, what is the dose? Okay, so we know we're trying to find the number of doses, so it's X for the doses. Then that would be in milligrams. Okay, then she weighs 56 kilograms, so that will go under X. On the other side is, of course, how is the cortisone dosed by normally? So it'd be 0.5 milligrams per 1 kilogram. So if you have kilograms as your on the bottom, you put kilograms here, so it'd be 1. Milligrams on top, 0.5. Okay, so then you're going to cross multiply. X times 1 is 1. 0.5 times 56 is 28. 28 divided by 1 would be 28 milligrams, okay, of the dose. Okay, now this example, if you flip back to page 96, it's going to be example, I'm just going to kind of go through example 4.4.2. Okay, so what it says is a patient, and it has 1 and 2 steps, so I wanted to show it to you again. A patient weighs 74 kilograms, that is to receive a medication of 0.4 milligrams per kilogram. What will the dose be? So that's going to be our part 1. The next set, if it will be part 2, if the medication is available in 15 milligrams per 10 milliliter solution, how many milliliters of the medication will the patient receive? First, we're going to do part 1. So we have, we're trying to find our dose, which is X milligrams. Patient weighs 74 kilograms. Okay. And then, of course, to receive a medication of 0.4 milligrams per 1 kilogram. So we know the 1 kilogram goes on the bottom because we have kilograms over there. Milligrams over here on top be 0.4 milligrams. You're going to cross multiply. 1 times X 1 times X is 1. 74 times 0.4 would be 29.6. Okay, so it is 29.6 milligrams of dose. Okay, then you're going to do part 2. Okay, next you're going to find your X milliliters, it says. And we know we have a dose of 29.6 milligrams. Okay, and then we have, of course, the medication is available in 15 milligrams per 10 milliliters. So it's 15 milligrams. Milligrams on the bottom. Both on top should be milliliters. So it will be 10. Cross multiply. X times 15 is 15, goes on the bottom. 10 times 29.6 is 296. Divided by 15 is 19.73 milliliters. Okay, so next we're going to do one with calculating doses, of course, based on your body surface area. So the measurement is based on weight and height variables. And of course it is going to be expressed in meters square. And they use nomograms, of course, to determine the BSA. So some medications are going to require the BSA to calculate a patient's specific dose, such as chemotherapy drugs. So here's your thing here. So if you look at this chart here, it is a nomogram estimating body surface area for children. Okay, the next one is a nomogram for estimating body surface for adults. Okay, so if you go through these steps here, steps for reading a nomogram and for estimating the BSA, is you want to first mark the patient's height on the left column, which we've done, 62 inches. Then you want to mark the patient's weight on the right column. So we have the right column here. And we have their height, which is or their weight is 162 pounds and their height is 62 inches. So step 3, draw a line or place a straight edge ruler on the 2 marks. Okay, and then you just draw a line. Where it meets in the middle, you'll want to read the BSA where the lines intersect the center column and read to the nearest 1/2 unit. So in this case, the BSA is 1.52 meters square. Okay, so first we'll do an example of this. So you look here, a patient, of course, is to receive a medication, of course, with a dose based on 50 milligrams per meter square. If the patient has a BSA of 0.90 meters square, what will the dose be? If the medication is available only in 15 milligram tablets, how many will it be dispensed? So first you're going to determine the dose again, and then determine the number of tablets to be dispensed. So with part 1, what you want to do is, since the dose is to be based on your 50 milligrams per meter square, multiply by the number of square meters of the BSA, in this case 0.90. So I can set it up as a ratio proportion, so I'll just do that. So if you have your 0.9 meters square, I'm trying to find your dose, X milligrams. And then of course you have doses based on the 50 milligrams per 1 meter square. Okay, so then you want to cross multiply. X times 1, remember always goes on the bottom, so it'll be 1. 0.90 times 50 is 40 times that is 45. So your dose would be 45 milligrams. Next, you want to determine the number of tablets to be dispensed. So we know we have a dose of 45 milligrams per one, and we need to find how many tablets. Okay, so then it is available in 15 milligram tablets, and that would be always per 1 tablet. Okay, so cross multiply. 15 times x would be 15. It always goes on the bottom because you multiplied it by x. 45 times 1 would be 45. 45 divided by 15 would give you 3 tablets. Okay. Okay, so here is another BSA dose example. So we're going to determine the dose and then determine the number of tablets to be dispensed. So a patient with a BSA of 1.30 meters square is to receive a medication with a dose based on 0.80 milligrams per meter square. The prescription is to be divided into 3 equal doses, so how much will each dose be? If the medication is available only as 50 micrograms tablets, how many will be dispensed? So first, on part 1, I'd like to set mine up in ratio proportion. So if we look at here, the patient, of course, has the BSA of 1.30 meters square. And we're trying to find the dose, which is then going to be in X milligrams. Okay. Then the dose is going to be based on 0.80 0.80 milligrams per 1 meter square. And we have our units the same on the top and units the same on the bottom. Then you're going to cross multiply. X times 1 goes on the bottom, be 1. 1.30 times 0.80 will be 1.04. Okay, then your answer is 1.04 milligrams, but then you want it in 3 divided doses, so you're just going to divide that by 3, and you should come up with 0.346 milligrams. Okay, then you have your step 2, so we're going to convert the dose in milligrams to micrograms, the units of the tables, by of course, using the equivalency of 1 milligram per 100 micrograms. But if you did not do that up front and you wanted to convert it over, okay, I apologize about that. My computer keeps freezing up. So part 2 is going to consist of 2 sections. First, we need to convert the milligrams over to micrograms. So if you did not know that 1 milligram equals 1,000 micrograms and we wanted to convert, I'm going to show you how to do that as a review. So you have 0.346 milligrams, and you want to convert it over to micrograms because the tablets are only available in micrograms. So X micrograms, milligrams here, have to have milligrams here. Remember, milli means 1,000, micro means 1,000,000. Okay, so if you want to simplify that, take 3 off here, 3 off here, and then you should have 0.346 times 1,000 equals 350 micrograms. So now what we've done is we've taken the 0.346 and converted it over to micrograms. Okay, and then next what we'll do here is we'll do the second part of number 2. And so you have, of course, 350 micrograms is the dose. We're trying to find X number of tablets. And we have, of course, it comes in 50 micrograms per 1 tablet. Okay, so then you're going to cross multiply. 50 times X, it goes on the bottom, it'd be 50. 350 times 1 would be 350. 350 divided by 50 will leave you with 7 tablets. If you look in your book on page 103, number 25, number 25, a pediatric patient weighs 23 pounds and is 32 inches in height. The manufacturer of acyclovir has recommended a dose of 250 milligrams per meter square every 8 hours. The physician has ordered 200 milligrams of acyclovir 3 times a day. Is the physician's order safe according to the recommended dose? So what you want to do is you want to take the pediatric patient's weight, which is 23 pounds, and her height, which is 32 inches, on that nomogram, and figure out her BSA. So when you do that, her BSA comes to 0.47 meters square. Okay, so next we want to figure the dose, and of course she's supposed to be I'm trying to find the dose here. You have X underneath milligrams, and you know her BSA is 0.47 meters square. Okay, then you look into the word problem, and it is recommended dose is 250 milligrams per 1 meter square. So then you're going to cross multiply. Whatever you multiply the x by goes on the bottom. So 0.47 times 250 should come out to be 117.5. So it's 117.5 milligrams. Okay, so if you actually look at, of course, the milligrams or the suggested dose based on her BSA, which is 0.47, the recommended with her BSA is only 117.5 milligrams. So the physician, of course, has ordered a dose higher than the recommended dose. Okay, because he's actually recommended 200 milligrams of acyclovir 3 times a day. So it does not meet, or is not recommended. Or you could say, no, it is not safe because he has ordered, of course, a dose that is going to be higher than what is recommended by her using her BSA. So calculating pediatric doses, and it is sometimes appropriate to calculate a pediatric dose using the normal adult dose. Anyway, there's 2 rules. The Young rule is based on years of age, and the Clark's rule is based on dose of weight. So the Young's rule, the formula used to determine an appropriate pediatric dose by using, of course, the child's age in years and the normal adult dose. So you're going to put on the top here age in years, and all you do is just plug in the numbers. The age again down here plus 12 times the adult dose equals your pediatric dose. So if you look at this example here, you have a 6-year-old child, so they put 6 here and 6 here. Dose of medication that has been suggested of the adult dose is 500 milligrams, so we put that there. So what you would do is you do 6 plus 12, okay, then take 6 and divide it by that, times that number by 500 milligrams, and you should come out with 166.67. The Clark's rule, of course, is a formula used to determine an appropriate pediatric dose by using the child's weight in pounds and the normal adult dose. So it's weight in pounds divided by 150 pounds times the adult dose equals the pediatric dose. So if you had a 80-pound child that needs a dose of medication that has a suggested adult dose of 250 milligrams, using Clark's rule, what is the appropriate pediatric dose? So you have 80 pounds of the patient, then you're going to divide it by 150, and then the adult dose is 250 milligrams, and it equals 133.33. So you always want to do your division first, then you're going to times that by 250, and then it will equal 133.33 milligrams. So this is showing you a comparison of the two if you with this problem. A 5-year-old child weighs 44 pounds, 20 kilograms. The normal adult dose is 650 milligrams every 46 hours as needed to determine the child's dose. So this is showing you a comparison of what if we did the years. 5 years here, 5 here, plus 12. Then you multiply that by 650, come out to 191.18. Clark's rule. You have that 44 pounds, because that's how much the child weighs, divided by 150 pounds times 650 would equal 190.67 milligrams. So if you look on page, or number 33, I think it's page 104. We'll do some examples. So number 33, a 8-year-old child weighs 68 pounds, 30.9 kilograms, and is to take acyclovir, which is a normal dose of 600 milligrams. So what you're doing is on A, you're going to use the Young's rule, and on B, you're going to use Clark's rule. So if you use Young's rule, you're going to put the age, which she is 8 years old, and then you're going to do 8 years plus 12 years. So when you do that, 8 plus 12 is going to be 20. 8 divided, and then you're going to put the adult dose, don't forget it, 600 milligrams. 8 divided by 20, then you multiply it by 600, equals 240 milligrams. Okay, if we use the Clark's rule, the child weighs 68 pounds, divided by 150 pounds. It was multiplied by 600, which is the adult dose, and it should come up to be 271.99. And if you rounded that off, it'd be 272 milligrams. Okay. So that's all of section 4.4. I apologize for my computer freezing up. If you have any questions, please just send me an email or come by my office and I'll be glad to go through some extra problems with you.